All right, let's start. So, welcome everyone. So today we will be continuing on with our neural network deep dive. So, likewise, we'll be going into deep neural networks. So, essentially, we'll be talking about what deep neural networks are and how to build a good deep neural network. So, in this case, we'll be using the estimation for obesity levels as a data set for this slides portion. And then later on, we'll go into a different data set when we actually work on the Colab notebooks. So, what is this data set? So this data set contains, I think it's 14, I could be a bit wrong about that, attributes with the goal to be able to predict the obesity level. There are, I think in this data set, about 7 obesity levels. There's underweight, normal weight, and then there's like 3 types of obesity levels. So there's overweight level 1, overweight level 2, obesity level 1, 2, 3, yada, yada. Meanwhile, we have with our attributes, we have gender, age, height, weight, family history, high calorie count. You guys can read the list. So I'll give everyone a little bit of time to kind of talk amongst yourself, and I'll ask 2 questions. One, if you were to try to predict someone's obesity level, given all this data, how would you do it? So this is just in your mind, how would you do it? And then the second part would be if you then were to make a machine learning model, what would you do to be able to predict this? So another person on Zoom, it might not be another person to talk to, but think about these things and I'll ask everyone in a couple minutes what they've come up with. So you can go on, talk amongst yourselves. All right, so we're going to have a open discussion here. So since like there's not too many groups forming, does anyone have something they would like to point out for that first question about how would they go about predicting? Any patterns you think you could see in this? One thing to point out for BC level, this is based on more than just BMI. This is also like your fat density, which is kind of hard to measure, which is why we have all these attributes. So any patterns you might like to look for here? Yeah, just in general, you maybe like, oh, the older you are, the more obese, things like that. So like the high calorie diet, so that can either be true or false. How would that like affect it? You would think, no.
I mean, I think it's like it's kind of based on the quality, like what you're eating. So obviously, high calorie diet. If you're eating like way more calories than you should get, like they'll have like a more positive correlation.
All right, yeah, definitely. So I think there's just a lot of things in this data set. And so kind of want to ask you guys the question. So how complex do you think we'd have to make of a model to be able to identify something like this, right? Something, I'll just give like 1 to 10, I guess, where 1 is very simple, 10 being it's almost impossible to figure it out, think natural language processing, complex things. What kind of numbers what kind of a difficult do you think this would be? 7? Yeah, that's a great answer because there's, first off, there's a ton of data, right? And the correlation between things, it might be a little simple, like, probably people with higher calorie diets might seem to have a higher obesity level, but, there's so many different edge cases and so many different combinations of these things that could be a bit different, right? It could be a little bit more complex. So if you were to make a model out of this machine learning model, what kind of model would you guys be looking toward? Well, I could tell you today we're going to be talking about deep neural networks. So that is a great way of modeling this. Again, there's other ways, linear regression and a bunch of others, but today we'll be mostly talking about deep neural networks. Oh, my clicker's not working. All right, so we'll talk about deep neural networks and mainly how to build a neural network, right? Because we've seen how to put it together, but what is the correct ways, or the correct ideas that we're supposed to be looking for to make these more efficient? So when I talk about a deep neural network, it's essentially the exact same thing as a neural network, except for it has multiple layers in terms of its depth. So we talk about how there's input layer, output layer, and then the hidden layers. This is either singular or plural, depending on how big you want to be. But when we're talking about deep neural networks, it's typically going to be multiple hidden layers. And that's kind of what defines what a deep neural network is. So difference between a deep neural network and a regular neural network is just the size difference in the amount of layers. So let's go into this example of that previous data we just saw. So we've seen this before from a previous meeting with the Colab notebook. We have our model definition. So what are the different layer sizes we want to put in the activation function? This one, just randomly came up with something. It has 4 different layers. It has 4 different hidden layers. I'll say that. It has one of size 10, one of size 20, then 100, then 50, and find the output of 4. Because I guess in this case, we're trying to classify the only 4 types of obesity. So they're all connected with just random activation functions, right? We just learned that activation functions are important, but we never really talked about when to use each one. So we're going to kind of go into how to kind of make this better. So we also have a couple loss function. We have a loss function defined here. It's mean squared error. It's decent. Optimizer we have as the stochastic gradient descent. We'll get more into that. Just know, kind of just put random parameters together. And let's say we ran it and we realized it wasn't as good as we want it to be. All right. So what do we do next? What are things that we should change? Because yes, we could just randomly roll the dice again and randomly change things. And that might work, but it's kind of not the best idea for building a neural network. So what is something that we should be looking out for? So this main thing that we'll be going over is the concept of overfitting. Overfitting essentially means when your model is learning the wrong things. So in this case, it's learning noise or just overall memorizing the training data. So if you can look at the diagram on the left or your guys' right, you can see that we have on the bottom probably an appropriate model for determining the difference between those circles and crosses. So, it's just a smooth loop. It's wrong sometimes, but that's what you would expect. No model is going to be exactly perfect. Underfitting, which is the opposite of overfitting, would just be a model that's a little bit too simple, not trained well enough, not defined nicely. And so you just get that single linear line. Meanwhile, overfitting would be something that memorizes that training data too much. It really looks at the noise rather than general patterns, which is where we see here with all those like really curvy lines that kind of look like it's really looking for those circles rather than just looking for patterns. And so this is what we'll see very often within our neural networks. And so what are ways that you guys think could help prevent this issue from happening, given this previous neural network? Let's say that's overfitting is an issue with us. What can we change about this neural network to kind of fix that issue? Just throw some ideas out. What can we change? Anything about the data we can do to help prevent this? Anything with the model? All right, well, there's a lot of things we can actually change. So we can start off just more training data, right? The more data there is, the harder it will be to memorize noise. It'll be more likely to find the general patterns. And obviously you can't always just say, I want more data, I'm going to get more data, or maybe even more data takes more time to train, therefore that's not a possibility. So what other ways? Well, one of the biggest things is reducing the complexity of the model. This could be either reducing the number of layers or hidden layers within the model, or reducing the number of neurons within the network. So both of those will help reduce the complexity and also help prevent this form of overfitting or memorizing that training data. Additionally, other ways of decreasing overfitting or overlearning, I guess, would be just to have it learn less, so less epoch, so it trains for not as long. And lastly, dropout. Again, we'll get to dropout in the next slide, so you don't have to worry about that. So far, is everyone following? Any questions so far? All right, well, move on. If you have any questions, feel free to raise your hand and I'll stop to figure everything out. All right, dropout. So what is dropout? Dropout is essentially removing or zeroing out random neurons within the network. So if you look on the diagram on the right again, we can see on the very top, that is a fully connected neural network. Very simple, every single neuron is connected to every single neuron in the next layer. Well, if we apply dropout, we take random of those neurons and kind of just get rid of them. You might be asking, why are we just getting rid of random neurons? And that is to also, again, solve that overfitting problem, but mainly it focuses on preventing co-adaptation. Co-adaptation is when multiple neurons on the same layer learn the exact same thing. So for instance, if we remember last week when I talked about predicting or being able to identify if a square exists in a picture, that let's say two neurons both get lit up or turned on when it identifies a vertical line. If we have two neurons identifying the exact same vertical line, that can result in some problems that come with that one maybe line having more of an importance or impact than other things that might need to be a bit more even. So we can use dropout to decrease the number of neurons and help prevent this existence of co-adaptation where there is multiple neurons learning the exact same thing, or these neurons have the exact same weights. We wouldn't want something like that. So let's go into the more mathy part. So in addition to just zeroing out those neurons, it actually also increases the weight or importance of the remaining neurons. And some very simple calculation for it. So you have a dropout rate. So this is the percent of nodes that you're zeroing out. So in this case of the diagram, we're removing about half of them. And the remaining ones that aren't zeroed out get multiplied by 1 over 1 minus that dropout rate. You don't have to have this memorized, no worries. Just you need to know that the lower the dropout or the more things that are dropped out, the bigger everything else will be multiplied. So think of it as making up for all the neurons that are removed, making sure everything else raises in importance or their numbers have a bigger impact. So let's go add dropout to our model. So you see here with the three arrows, we can see we added those dropout. We added dropout to those layers. So if we look at the first one, is at the layer of size 20. So if you look at the diagram, I don't know if you can see it very well, but that would be that orange layer. And so we notice that there's some X's there, and those X's kind of just remove the randomness of dropout, removing some random neurons. Same thing with the 100 size layer and the 50 size layer as well. Each one of those has a dropout layer that we added here. So we might run this again and say, hey, look, we either may have seen a improvement in the prediction, maybe not. Again, these are all things that could help or things to look forward to when trying to improve your model. So that's a pretty start. Maybe helps, maybe not. And so a lot of things we'll be talking about are rules of thumbs that you can follow. You don't have to follow it. Sometimes not following it actually makes it better. Just the general consensus of the community that puts these things together. So next, we talked about to remove overfitting, we have to be able to make our systems less complex. So this might seem to get a bit, you might see some things that collide with each other and disagree, but we'll talk about those when we get to that. So the depth, what do we talk about by the depth of a neural network? The depth is essentially just how many layers a neural network is. Width, on the other hand, is the number of neurons per layer. We'll get to that later. So the general rules of thumbs for determining how many hidden layers you might need kind of goes around the following. So if your data is linearly separable, that means the result is like a linear equation from the given data. So think in a linear regression situation where you just find the best fit line, you would not need any hidden layers. It's just simple. You have your input and you have your output. No other layers needed, and it'll predict just. However, if you add a little bit of complexity to it, so maybe it's not linearly separable, things kind of depend on one another, you might want to add 1 or 2 hidden layers. Things for that aren't too complex. The majority of things can be solved in just 1 to 2 layers. However, once you get to those large dimensions with increasing complexity, that's where we want a little bit more, maybe 3 to 5 hidden layers to be able to solve these problems. The more layers you add, more complex. And if you go even higher, above 5 hidden layers, or even up to 8, that's where we start to see more issues with overfitting is almost guaranteed at that point, unless there's these very specific models. But generally, you want to keep the number of layers not too high. It really just depends on the complexity of your model. So here are kind of examples as to what each hidden layer means. If you look on the right, this is just for visual interpretation, doesn't actually mean too much, just for something that helps you guys figure everything out. So 0 hidden layers, again, linear separable functions, you'd use that for that. If you have 1 hidden layer, it can essentially estimate any continuous mapping from one finite space to another. It's essentially, it can be able to create any boundary between two things. And the thing is, there are a couple theorems that require like things being infinite numbers, but there are theories saying that you can create any neural network or any good neural network out of something with only 1 hidden layer. It might not be the optimal neural network, but essentially you should be able to create everything with just 1 hidden layer. Not something you would always suggest, but something that you can do with a certain amount of neurons. On the other hand, 2 hidden layers can represent any arbitrary boundary to arbitrary accuracy. Essentially, you could do anything with 1 hidden layer, but a little bit more accurate. It might not be exactly like this. Again, all rules of thumbs, these things aren't exact, just kind of estimates. Sometimes 1 is more accurate than 2 and vice versa. And getting beyond 2 gets even more complicated with how much it actually does train or even overfit your data. So as we talked about before, when we went to how complex our model was, we said about 7, right? We'd say, it's definitely has some complexities to it, but it's not the most complex thing. So we probably don't need all 4 hidden layers. So we see here, we did remove a couple layers. In this case, we removed the layer size 10, layer size 100, just chose 2 random layers to remove. And now we're left with this. We run this, maybe it's a little bit better, maybe it's not, but we realize we still need to do some improvements in this. So let's continue on to make this a better neural network. So is everyone following so far? Any questions? All right, cool. So now we'll go on to the width. So how many neurons per hidden layer? So how do we figure this out? Again, there's no perfect way of figuring this out. It's all, rules of thumbs, playing around. Some might work better in some situations. But generally, people say that you'd want the size to be about in between your input layer and your output layer. So if we look at this diagram on the right, we see that the input layer is of size 6 and the output layer is of size 1. So we'd probably want our hidden layers to be about something in between. So as you see here, 4 and 3, somewhere in between 1 and 6. So when in doubt, kind of the people say, hey, if you don't really know, you might as well just try somewhere pretty close to the middle. So, between 6 and 3 is about 3 and 4. Yeah. And then if you want to follow more distinct equations, you can follow the one here. It's the number of hidden layers is equal to the total number of training samples. So that would be like if you had 1,000 instances, you put 1,000 at the top, divided by some arbitrary constant between 2 and 10. This is one of those things where you can kind of choose and play around with it. And times the size of the input layer and the size of the output layer. So for instance, if we had 500 training samples and our input size was 6, or our output size was 1, and we set our alpha constant to 5, because some random variable between 2 and 10, we get 500 divided by 30, right? And that is about
17.
What do you say? 17. So you'd probably want, about 17 neurons. Again, just a rough estimate, doesn't have to be exact. In this one, we have a lot less, right? And so there's a bunch of different rules here that you can go into play. Another thing you want to keep in mind is typically you would want your multi-hidden layer neural networks to actually decrease in size as you go on. So maybe the first hidden layer is a larger one, and it gets smaller and smaller. Again, just rules of thumbs. Other rules you might like to look through is number of hidden neurons is equal to 2/3 the number of input neurons plus the number of output, or the number of hidden neurons is less than 2 times the input size. Again, these are just rules of thumbs. You don't have to follow them. If you don't know where to go, these are kind of the best things to try out. And one key thing to note is that if you are building a network and you're saying, hey, should I do more layers or should I do more neurons per layer? It's generally better to go with a larger depth, meaning more layers than it is more neurons per layer. So just something to keep in mind if you're coming up with these things. to go with a larger depth.
Specifically, just to clarify, the reason that you want to go large depth over large width is because it computes faster. This is just straight up the whole answer. The reason is you can calculate the number of parameters or just trainable weights that you're going to need to have between each layer. So from the input layer to the first hidden layer, you have 6 input layers times the 6 input neurons, times the 4 hidden neurons there. That's giving you 24 total parameters because every neuron in that layer is connected. And then you're going to add a bias term to each of the neurons that's in the first hidden layer. So it's a total of 28. Now, if you made it 60 large, you're going to do the same calculation, but do a lot more of it. So if you can get similar performance by just making the network longer and thinner, it is a lot faster to just make it longer and thinner than make it wider, even though it is possible to compute any function in one layer. Make sense? All right.
I like to point out that you do not have to memorize these equations. Just kind of get the general feel of it. And again, you can always look these things up later, so no worries about having to memorize any of these things. A lot of the equations here are just kind of for your reference and just kind of keep in mind. So let's modify our neural network to kind of follow those rules we just figured out. So as we see here, we've decreased the size of each of our layers, right? We started off with a 20/50. Now we are changed to a 10 and a 7, which makes a little bit of sense, right? Because if we have our input of 16, output of 4 kind of averages around that range of 10 to between 10 to 7. So we start at 10, and we go follow the rule of, make it decreasing size to about 7, and finally have our output of 4. Keeping in our dropout layer, our final layer. Again, we're just trying things out and seeing how it works. Maybe again, it helps, maybe even it hurts our model. We don't really know until we try it. So if we want to continue going, well, it's the next thing we can change. Next thing we can change is our activation function. So previously we did talk about activation functions, but we didn't really get into why we need them or what exactly they do. So the main reason we need an activation function is for their non-linearity. This essentially just changes up how each layer combines together. So if every single layer was just connected through this linear function here, so as if there were no, connected through this linear function here, every single layer would be linear. So one weird thing, the way you can think about it is if you had a linear function and you inputted it another linear function, and then you inputted that another linear function, and you just had this complex thing of a bunch of linear functions within each other, that could just be compressed into just a single linear function. So essentially, if we have a neural network that is just connected by a bunch of linear activations, it's equivalent to a single layer neural network. And because of that, we actually need these hidden layers or hidden activation functions to be able to prevent that from happening. So we include all these activation functions. So for including activation function in your hidden layers, we suggest these 3 here: the sigmoid, tanh, and the ReLU activation function. We'll go into a bit which one to choose and why, but just know that we have our sigmoid, which allows us to follow this 1 over 1 plus e to the power of negative x function, which has a range of 0 to 1, and then the tanh, 0 to negative 1 to 1 range, and then ReLU, which is just the max of 0 and the thing you're putting into it. These are all ways of adding some non-linearity to these layers. If you look at the bottom left, we could see kind of a graph to show which one you would want to be using. And we see we pretty much want to be using ReLU for multi-layer perceptron. So the neural networks, for instance, we would typically want to use ReLUs. We'll get to why ReLUs is superior later in the next slide. So you also need an activation function at the very end. So not only do your hidden layers need activation functions, your output layer also needs an activation function. And so there's 3 right here that we would suggest. You have your linear one, which is fine in this case, since it's okay to end with a linear activation function, a sigmoid, which we already talked about, and a softmax. Softmax is pretty simple. It essentially takes all the numbers that come into it and decreases the size of all numbers or increases it such that the proportions of it stay the same. So for instance, if you have something with 3 outputs, you have a 3, a 2, and a 1. Throwing it through a softmax would change it to become that 3 becomes 0.5, 2 becomes 1/3, and the 1 becomes 1/6, so that they all add up to 1. However, the proportions stay the same, And so that's essentially what softmax does. It keeps portions the same, but makes it so they sum up to 1, just for easier viewing purposes. So depending on your problem, you might need to use the sigmoid, you might use the softmax. You can see in the diagram on the right side about which ones you might want to try out. Again, these are all rules of thumbs and don't necessarily need to be followed. So, we talked about ReLU being really important. Well, that wasn't always the case. Prior, like 1950s, the sigmoid function was considered the best activation function for hidden layers. And we can see that on the top right. But later on, we realized that the sigmoid function and the tanh also had this problem of what's called a vanishing gradient. Essentially, the more layers we add, the gradient slowly starts to disappear. Because if we look at the range of the sigmoid's derivative, or the gradient, we can see it's anywhere between 0 and 0.25. Meaning, if we had multiple layers of sigmoid activations, the further layers we go, that gradient would exponentially decrease. So maybe that first layer had a 0.25 gradient, but then that second layer has a gradient of 0.25 times the previous layer, which was also 0.25. And so we could see how fast that can eventually go to essentially nothing, meaning that the earlier layers will not get trained very much if we use that sigmoid activation function. So this is where the ReLU comes in. As we can see, the ReLU function has a derivative that's either 0 or 1. So if we have multiple layers, we don't actually have this vanishing gradient problem where eventually the gradient becomes 0. It's either going to be a 0 or 1 throughout the entire neural network. So we can then apply that to our neural network, all these activation functions we used. And so our problem is, again, a multi-classing classifier. And so we'd want to use a ReLU with a softmax at the end. So we'll stick in ReLU for all of our activation functions in the hidden layer, and then a softmax for our activation function for the output layer. Again, you don't have to necessarily memorize these. You can always look them up later. These are just keep in mind when you're coming up with these things. You can always look back at the slides or figure these things out later, but we'll go back. So any questions here? Everyone understand activation layers and why we need them and why we might choose different ones over others? All right, good. So let's move on. So what are the next things we can change? Well, we have our neural network built, right? We've done all the changes to it. There's a little bit things we can still do to it, but we'll move on from there. What are the other things we can change about our neural network? Well, we still have our loss function optimizer to play around with. So let's go in and talk about those. Loss function. So there's a bunch of different loss functions we can choose from, but essentially this talks about how accurate our model is, or in which direction do we want to actually optimize our neural network to be towards. So different loss functions will affect how our model trains. So the one we talked about before was the mean squared error. This was very simple and used very commonly for regression tasks. So mean squared error is pretty simple. It is the average of the squared difference between that predicted value and the actual value. So if we had a predicted value of 7, the answer was 8. The difference between that would be 1. You would square that, which I guess is also 1. And then you would find the average of doing that through every single prediction. So, well, why would we use this? One of the cool things about it being squared is that there's a larger penalties for outliers. So I mean, the farther away the prediction is from the actual value, the worse our loss function is going to make it seem, right? And so this way, if there's a lot of outliers, it kind of is bad for the training model, as it just kind of get all over the place. So sometimes it's not good, but if you have a regular amount of outliers, it should be fine. On the other hand, we have the mean absolute error loss function, which is very similar to the mean squared error, but instead of squaring the difference between the true and the predicted values, it is just the absolute value. And so as you can see here on the right side, that's what the different diagrams will look like. And the outliers are not going to be punished nearly as much as they would be for mean squared error. But that also means that it's more robust for these outliers. So if you have a lot of them, your loss function might not go as crazy as it would if it was the mean squared error function. Those two are pretty good for regression, but when it comes to classification, the main ones you want to be looking at is what's called cross entropy loss, or binary cross entropy loss, or multi-class, depending on what problem you're actually trying to solve. So What does entropy mean? Entropy essentially means the probability of something being the case. You don't have to memorize this equation again, just know that the general gist of what it's talking about. So we see here for the binary cross entropy, it takes the negative sum of the actual case times the probability that is correct, or that as the actual predicted answer. Then also adds it on to the exact opposite. So what's a chance that it wasn't the case and vice versa. So that's what you use for binary classification. And for multi-classification, you would just use the multi-class version, which, as you can see, they're very similar, just without that last part about looking at the opposite case. So we have these 4 loss functions. There's a lot more. You can look them up if you want, but these are kind of the main ones you would want to use. So if you want to use our example of the estimating obesity, it is a multi-class classification issue. So we would probably want to use the multi-class cross entropy as our loss. So what about the optimizer side of things? Well, we all learned about what gradient descent was in the previous meeting. So we should all kind of have a sense as to what that means. It's essentially just a very basic use of the gradient to identify where we want to go. And let me just tell you, that is a very slow way of calculating these types of things. Not very fast. There's a lot better ways of doing it. And so we'll go through the different types of optimizers that exist. I'm going to very briefly go over them because there's a lot more math behind it, which I don't think we need to go into, but we can start off with the first iteration of the optimizer list. So next we have the stochastic gradient descent. This takes everything that important about gradient descent, but allows us to take a random sample of that to apply the derivative. And therefore it's going to be a little bit faster to calculate. And using stochastic gradient descent, we can calculate our weights significantly faster than just the regular gradient descent method. The next we can add is momentum. Momentum allows for the weights to be changed in relevance to not only the current derivative, but the previous gradient calculated in, let's say, the previous epoch or previously. And so the reason why we want to use that is, again, to get over hills of local minimums, as we showed before, but also be able to converge much faster. So imagine if something's oscillating up and down, eventually you'll get to the oscillations will get a bit smaller. The momentum allows it to slow down just that much faster. It's okay if you don't fully understand it. This is just listing a couple things off that exist. So next one we want to add is adaptive gradient descent, or also known as ADAGRAD. ADAGRAD essentially uses the same concepts as the stochastic gradient, but will also change the learning rate depending on its past observations. So if it notices that something has the potential to learn much faster, it will increase the learning rate so that weight learns much faster. And so it's able to do this on the fly, allowing it to learn much quicker and converge in a faster way. Next one is the root mean square propagation, or the RMS prop. It is, again, an add-on to the stochastic gradient descent method, and it's able to notice which parameters cause that oscillation within the loss function. So it might notice that, hey, when predicting the color of a fish, or when predicting the classification of the fish, so whether it's a trout or a goldfish, the color might cause the oscillation of the loss function to oscillate a lot. So it might start to penalize that kind of color attribute a bit more. And so it's pretty smart in that way, and that is the RMS problem. The main one I would like everyone to kind of take out of this list of optimizers is the adaptive moment estimation optimizer, also known as ADAM. This is kind of the default for all data science, all machine learning models to use this optimizer. In the short sense, it is just a combination of ADAGRAD and RMS prop with some extra mathy stuff to it. But just know that you almost always will want to be using the ADAM optimizer because it is just that much faster at converging than those other optimizers. Again, these are all rules of thumb. So sometimes the ADAM optimizer optimizes too fast and you get the wrong value. And you might want to try out some of these other optimizers. Again, just things to play around with, but in most cases, ADAM's the way to go, or at least versions of ADAM, as you'll see when playing with code. So we can implement that into our model. And so we can see, hey, we've changed our loss function to cross entropy loss and our optimizer to be using the atom optimizer. And so now we have this new model that hopefully works better than what it did from the very beginning. Most likely it'll work about the same, but there's just so many different things you can tweak and play around with. This is kind of the general direction you want to be looking at. One quick note I'd like to point out, specifically for PyTorch, the cross entropy loss function includes the softmax activation function within it. So if you were going to use the cross entropy loss function, you wouldn't need to use softmax. Just a quick note putting out there. It's okay if you don't have to memorize that. We're all good. So those are kind of the main ways you can tweak a deep neural network or just any neural network to kind of look for a way to make it better or to make it even faster in the training methods. So again, these are just some of the things you can change the neural network to make it better, but there's just so much more you can do that I don't have the time to get into. There's neuron pruning, or removing neurons from the model, similar to the dropout, weight initialization. So at the very beginning of your neural network, what is the weight values equal to even before you start it? So maybe it's randomized values or you set them all to 1. There's data normalization. So starting off with, instead of age being any value between 10 and 90 years old, it's shrunken down to 0 and 1, maybe kept the same proportions or something. Gradient clipping and a lot more. There's plenty of different ways you can play around with these neural networks to see if you can improve their accuracy or their speed. Haven't got to cover them, but that brings us to the workbook section. So I'd like everyone to follow this workbook URL, and we'll start playing on predicting forest cover type. This notebook, you'll notice, is very similar to last week, so I'm not going to walk everyone through it. The main goal of this notebook is for you guys to play around with different sizes of neural networks. How many layers do you want to add? How many neurons per layer? What activation function? What loss function? All these things. It's mostly for you to play around with it, see what works, what doesn't, and to overall be able to just play with it rather than, build it from scratch, from having to create your own loss function or anything, just so that you guys get some experience tweaking these values. So I'll give everyone kind of almost the rest of the meeting. So what time is it? 6:42. We'll give everyone about 15 or so minutes to play around with this workbook, change values. Everything should be set up the same way. If you don't understand something, you can read some notes we added to it. Look at all the links. Those documentation links will all be helpful. If you have any questions, feel free to raise your hand. And good luck. We'll see how accurate everyone's models can get.